Here's another video introducing Newton's second law. You can take a look at the picture here and see what's happening. We have a ramp where there is some friction now. It's at a certain angle. We have a mass. We have an applied force F. We're told that this is sliding upwards. And what we want to do is derive an expression for the mass's acceleration up the ramp. So the first thing we do in a case like this is we draw a free body diagram, which we represent as a dot. And now let's draw the forces that apply. So we have the force of gravity, m times g, which acts straight downward. We have the applied force F that acts up the plane like that. We have the normal force, which acts at right angles to the surface. And then we have kinetic friction. And we know it's kinetic friction because this object is sliding. And kinetic friction is always going to oppose the direction that the thing is moving. So that means our kinetic friction is going to act in that direction right there. And the kinetic friction force is always equal to mu sub k multiplied by the normal force every time. And we need some sort of coordinate system here. I'm going to call positive upward, whatever way it's accelerating. I like to call that the positive direction. And we can still call this the y direction. The fact that that's not a right-handed coordinate system doesn't make any difference. As long as we're consistent when we write each of our equations, we're going to be fine. Next, we're going to use Newton's second law. Let's sum the forces in the y direction. And what would those be? I'm seeing Fn minus mg cosine theta. One more time. Theta, the angle of incline, is numerically equal to that angle right there. So Fn minus mg cosine theta, according to Newton's second law, that should equal the mass of the object times the acceleration in the y direction. The acceleration in the y direction is 0, which means that the normal force is equal to mg cosine theta. Now, why did we find that? Well, we found it firstly because we can, and secondly because we often need the value of the normal force, because you can see even here, there's the normal force right there connected to the coefficient of friction. So we need an expression for the normal force, and this equation here is going to get that for us. So we're in good shape. All right, let's write a Newton's second law in the x direction. I'm choosing up the plane to be positive, so applied force F minus mg sine theta. That's the little bit, I'm not going to draw it in, but you see where my marker is, right there. That's mg sine theta, that little guy right there, and he points in the negative x direction, according to my coordinate system. Similarly, what also points in the negative x direction is mu sub k times the normal force. That is the sum of the forces in the x direction, and that should be equal to the mass of the object times the acceleration in the x direction. Now, we can't cross that off to equaling 0 because this mass is accelerating up the plane. What do we know here? F is known, mg theta, mu sub k, normal force, we are not given, which is why the work we did just a second ago is going to come in handy right there. And then we're going to divide through by m. We could simplify this in any number of ways, but basically it looks to me like we're going to get an expression that looks like this: F minus mg sine theta minus mu sub k mg cosine theta, all of that divided by m. You could factor out an mg from part of this term. You could divide an m out in part of it. That's fine. There are many ways you could simplify this, but without wasting your time on this video, that would be an acceptable expression. in my book.